So the Drax EcoStore project, Peter's talked about that this morning. I won't go into detail with this, just a brief summary there. That 3 times 650 megawatts, and what's very interesting perhaps is 25,000 tonnes per day of biomass that will burn with 3 units. So we're currently burning 2/3 of that. That's an awful lot of biomass to handle in a day, an awful lot of trains coming in and out. And 450,000 cubic metres of biomass storage, or 320,000 tonnes. So that very large facility, that very large project, presents an awful lot of challenges. So what I've done, I've just concentrated on 3 key challenges that we can talk on in a bit more detail then. So these 3 challenges, first of all, of course, fire prevention and protection. But I will go into a little bit more detail. We've heard a lot about CO monitoring. Biomass evolves CO all the time. It off-gasses huge amounts of CO. The real question is, can we differentiate between normal off-gassing and the onset of combustion? So what I'll do is perhaps just show you what we're doing at Drax at the moment. It's not the only way of doing it, but it's the way that we're trying to differentiate between what's normal and what's not normal and what's could be a fire. Explosion protection, again, on such a large scale, is pushing the boundaries, and I want to talk to you about what we've done there. Explosion prevention and fire prevention are very closely linked for obvious reasons, but the explosion protection is quite different. It can interact with the fire protection, a point that Declan made this morning. I'll try and cover that one, Declan. We did consider it. And then with such a large storage reclaim is obviously potentially quite challenging. We've heard a little bit about the vibrating floor. I've got a short animation that will show you how that works. So we'll cover those three areas, the 3 key challenges. Fire safety, I apologise for using a picture that you've already seen. The sad truth is I've got quite a collection, so I'm not spoilt for choice in terms of biomass silos on fire. This one's brand, I think, but there are plenty of others. So it weighed very heavily on our considerations in the design. It's well known that pellets do self-heat during storage. One issue we've got is just how much do they self-heat? How do you predict it? How do you measure it? There's some quite well-established basket tests, isothermal basket tests, that not particularly suited to pellets. I think that's fair to say. But in any case, think about the extrapolation. If we extrapolate a basket test, 25 millimetre cube, 40 millimetre cube, 50 kilometre cube, we're going to extrapolate that by a factor of 9 billion, if my calculations are right, to get to 112,000 cubic metres. You know, is that credible? Would I be comfortable using that as a basis of safety? Not really. Now, we were very lucky. Peter mentioned that Drax started this journey 10 years ago, and certainly for 2 or 3 years in advance of Shepherd commissioning this biomass facility, they've been stockpiling biomass. So they've been stockpiling biomass around the country, gradually building up their supply chain, because they've got to match their consumption, or match the supply chain to their consumption, so they needed a bit of a buffer. So we had access to some full-scale stores, some larger stores. So we weren't talking about extrapolating from a 50 millimetre cube. We were actually talking about extrapolating from significant size stores, perhaps with 10, 15, 20 metres of stockpile depth. And we were able to work with Drax, get those instrumented, and actually get some real full-scale experience, which has definitely tempered our judgment. We've used it alongside the basket tests, but what became very clear from that, if you take those self-heating properties and you punch in the storage volume that we're looking at, whether or not it is proportional to volume, or as I think, proportional to storage height, you've got a problem. And that problem is we will be storing pellets that are dangerously close to the critical temperature, or even storing pellets above the critical temperature, which means that we can expect that they will heat up in storage. So how to deal with that? Other key considerations, you've heard, I think it was maybe John from one of the ports talking about recirculation. What do they do if they get product that's heating? Feels a bit counterintuitive to start moving the product. You expose it to more oxygen. But the truth is, if you talk to the owners of these stores or the operator of these stores, that's what they do. That's what the Drax store owners were doing. They did get some self-heating, and they did tend to mitigate that by moving the product. And I think that what demonstrated to me was that the heating effect can be very, very localised. You can actually see how localised it is when you see the mushrooms appear on top of the stockpile, which is where the moisture is being driven up like a candle, and the pellets are expanding due to the moisture. You actually see a mushroom form above the hotspots. So these nests of heating product perhaps are broken up in the handling operation. So yes, you introduce a bit of oxygen, but you also break open the protective cocoon, because of course it's such a fantastic insulator. So recirculation was something we seriously considered at Drax, but we chose not to do. So we don't feed dome to dome. Why not? Well, because we can empty a dome, 112,000 cubic metres, in 24 hours. So we can actually burn it. So I think if you detect the problem early enough, the preference is to get rid of it. So provided the downstream handling equipment can cope, and we can cope up to about 100 degrees C, the preferred option is actually to burn it. And I know if we do get the odd hot load notified by the ports, we can bypass the storage and we can go straight to the boiler and avoid storing hot product. Alternative disposal routes is something that, again, we thought long and hard about, because nearly every one of the pictures that I've collected of these silo fires feature something like that. If it's a concrete silo, it typically features a pecker with a fire brigade knocking a hole through the side of the silo. If it's a steel silo, it's typically somebody with a cherry picker and some angle grinders cutting a hole through the side of the silo. And I don't know about you guys, but if that was a silo on fire, generating all kinds of fire gas, I'd rather not be doing that. But it surprises me how often that's what the fire brigade have to do. They have to cut a hole through the side of the silo. So we made sure that we incorporated an igloo door. We call it's actually a double door system, but it does allow access for a front loader to remove the product. And again, experience from a number of stations in Scandinavia where they've had fires, they've managed fires, is they've actually managed to recover huge amounts of the fuel and actually store it outside for 6 months in the rain and reuse it, which is perhaps interesting, but it does show how the biomass behaves with water. It forms a crust, and that crust can actually protect the pellets quite well. So they lost the first 300 millimetres, that just degraded back to sawdust, but the remaining pellets were actually usable. But the point is, if they had an option to get the pellets out, they were able to take it out and actually recover some of the fuel, reuse it. So then we'll have a look in a bit more detail, let's say, at fire prevention and protection techniques. And the protection techniques often rely on detecting the fire early enough. And how do you detect a fire in a store? How do you detect self-heating? That's what we'll be looking at. So in terms of fire prevention, a key preventative measure is tramp removal, tramp metal in particular. We have various stages of removal. We start off with a coarse screen at the rail and load facility. We then go through some rotary disc screens where we bring the size down, and then pass it through overband magnets. These again presented a challenge, 2,800 tonne an hour separation, not easy. We had to split the stream into two to keep it to a workable size. And I think a point to note is even at 1,400 tonnes an hour, an overband magnet doesn't have a fantastic efficiency with relatively small nuts and bolts. it'll probably pull out the bigger pieces of tramp, but there will still be tramp metal getting through the system. So you do need to keep this in mind. Monitoring on the conveyors really is a key part of the Drax philosophy, and I think looking back through the history of some of the silo fires, I think a lot of them could have been mitigated, if not prevented, if they avoided transferring burning or glowing embers from one inventory to another, whether that's the ship to a silo or a silo to a silo, a store to a day silo. So we put a huge amount of effort into monitoring on the conveyors. So we monitor for heat, and these are the most reliable of detectors. They've certainly encountered hot product, not on EcoStore but on the co-firing system. They have worked in pulling out hot product before any flame detectors or spark detectors picked out the same problem. The downside of the heat detectors is they really require a moving belt, so they need the product passing underneath the detector. So we use those in conjunction with flame detectors. The flame detectors have got a range of maybe 20 metres, so by arraying those every 40 metres, we've got full cover of a static belt, because the concern was we'd get some hot product in, it'd be on one of the parked belts, and it gradually continue to heat and potentially catch fire undetected by the heat detector. Spark detection, important part of the protection. Whenever we turn the product over at a transfer, it's dropped vertically, it's an ideal opportunity to do some additional detection, firefly in this case, at all transfers. I've lumped the last two together, in-vessel temperature monitoring and exhaust gas monitoring, because for me they do sit hand in hand. We have 82 temperature monitoring points in each dome, but that's near as damn it an 82,000 tonne dome, so that's a monitor point per 1,000 tonnes if you're lucky, and I won't be that lucky. We'll have potentially these small nests of heating product that I mentioned that remain relatively undetected. What I hope we will pick out with the temperature probes is the average temperature, and what we'll start to see is upward, downward trends. Now the temperature probes, I've just picked out 4 sensor positions here, just to prove they're working on this particular day. They're probably about 20-25 degrees C. But what we can do is we average the temperature of each dome, and we use that in conjunction with the exhaust gas monitoring. So we monitor for oxygen depletion, we monitor for carbon monoxide, carbon dioxide, methane, and half a dozen other fairly exotic gases I can't ever remember the name of, but wrote them down, aldehydes, phenols, etc. The problem with all these gases, they're all present during normal off-gassing, and they're all present during combustion. So how the hell do you differentiate between the two? How do you know what's good? So I'll try and explain that. This just a little bit more information on this this slide. This is the actual dome contents, and it's the average. This is actually the carbon monoxide level. This is the oxygen depletion. So what happened there? Well, we actually didn't fill the dome because you can see the level was dropping, but we did run the fans. So we have some fans on top of the domes that allow us to change the atmosphere. So chances are we're doing some maintenance on the dome roof, and whenever we're doing maintenance on the dome roof, we do run the fans to draw any leaking carbon monoxide or nitrogen away from the conveyors. But that pattern is quite interesting. What we'll see is whenever we fill a dome, the oxygen content will rise inevitably. We've got the valves open and we're pouring in new pellets, bringing new oxygen. But we can generally keep within 10% oxygen. So we're typically running at 95% nitrogen, 5% O2, and even without rotary valves on the inlet, which are just not practical at 2,800 tonnes an hour, we can actually keep very close to being below the explosion limit for biomass. So in terms of actually developing some solutions, Drax made it very clear to us that these domes were for long-term storage. Yes, we can empty one very quickly, You can empty one in 24 hours, but they are the replacement for the stockpile. With a coal stockpile, they've got months of security. With a dome, at normal burn rates, they might have 13 days for 4 domes. So you can see how hand-to-mouth they are with the ports and the supply chain and logistics. But they do want to keep the products in there as a long-term store. And we know already that the critical temperature for those domes, I don't know whether it's 60 degrees, 65 degrees, but it's certainly very close to the likely delivery temperatures. So that influenced the decision really to store under inert atmosphere. So the domes are maintained at 95, 96% nitrogen, the remainder being predominantly oxygen. And we generate that nitrogen on site using a pressure swing absorber, which is shown in the photo there. That's backed up by a liquid nitrogen system, so you can see the liquid tanks, and the next slide I think shows the next picture shows the evaporators. So the liquid nitrogen is evaporated using atmospheric evaporators and then pumped into the domes through the bottom. We'll have a look at that in a bit more detail. And that's done pretty much on a continuous basis. If perchance the domes are fairly empty, 5, 10, 15 metres of fill, they might have the nitrogen switched off. But as soon as the domes get full, the nitrogen is on, and it's on all the time. We also have a CO2 blanketing system, which is part of the armoury for firefighting. The CO2 is added in liquid form, so 2 of those tanks are actually for liquid CO2. I suppose technically it's added as a solid, because CO2 being CO2 will turn to a solid when we drop the pressure. So it's added into the domes as snow. So we have snow horns, snow generators on top of the domes, and that's a chosen method of blanketing a surface fire. I think it's fairly clear to me, looking back through the catalogue of biomass fires, that we do have deep-seated fires that probably are best dealt with nitrogen added through the bulk, but there are also a number of surface fires, and certainly the Drax fire in the co-firing silo was a surface fire, and it was actually extinguished with water. So I wouldn't rule out water deluge. I think it's a really important part of the armoury. For me, it's the primary protection on the belt conveyors. If we pick up a problem on the belt conveyors, we hit it with a deluge, and that's the end of it. Of course, it'll need some manual intervention to remove the deluge pellets. We'll foresee the fact that they'll swell, and we'll make sure that we design the conveyors accordingly. But that is the primary protection on the conveyors. It might be third on the list for the dome or even the boiler distribution silos, but I think water has got a part to play. Definitely for a surface fire, definitely for cooling the roof structure during firefighting. And coming back to your point, Declan, about did we consider a fire following an explosion? Yes, we did. I think the feeling is that the most likely scenario is that a fire would lead to an explosion. So a lot of emphasis on fire protection. You've got a fire in a dome, there's a definite possibility of an explosion. We'll come on to why we chose to vent the domes as well as inerting them shortly, but that was the primary consideration. But we did also think about, what if it comes the other way around? What if we have an explosion that blows the top off the dome, an explosion vents, and then maybe it doesn't nullify our fire protection systems, but it certainly makes them work a lot harder. Nitrogen going in through the bottom should be relatively unaffected in the bulk. Yeah, of course the headspace is going to be pure oxygen, but actually pumping the gas through the base is still going to be beneficial. If I've had an explosion, I've lost the roof of the dome, then the chances are we're going to hit it with a water deluge. And so that should still be active with an open top. And again, CO2, yeah, that might be pretty much useless. I suspect the updraft from the flames would whisk the CO2 away very quickly. But we did consider that scenario, but the most likely one, I think, is a fire leading to an explosion. And self-closing vents just weren't practical on this scale. We talked about spark detection at every transfer. We actually have spark suppression at key chutes, and the key chutes are the ones that enter the vessels. So this is really our last shot at trying to stop a glowing ember dropping into a vessel. We've tried for heat detection, we've tried for flame detection. At the last chance as it goes into the dome, we have a fire suppression system that, touch wood, hasn't operated at the moment. So a closer look at the nitrogen distribution system. Rob mentioned this morning segregation during filling. These are core flow stores. That's a fact. You know, we empty 85% by gravity, and then we reclaim 15% by operating the vibrating floors afterwards. So they're going to flow in core flow, and you can see here slightly different hatching. It's not too clear, but we anticipated that those would be in the flow zone, good clean pellets. I guess I could dream. I could dream, but maybe one day. But we certainly anticipated that in the non-flowing zones that we would get significant fines increase. The primary mechanism being segregation during filling, this rolling segregation that Rob talked about, and what we would get is a significant increase in fines here and here. And that was a concern, of course, because introducing gas at the bottom of the dome, what I don't want it doing is taking the easy route and just going up through the flowing channels and bypassing the very areas that are likely to self-heat. So what we had to do was look a lot more closely at nitrogen distribution. More of that in a second. The nitrogen generators generate 2,800 metres cubed per hour of 96% purity. And that's certainly proving enough to serve 4 domes. So we actually cycle round the 4 domes, and we can hold those 4 domes comfortably at 4% O2. But that isn't felt to be enough for firefighting purposes. Now, in terms of what is enough for firefighting purposes, the best we could do, and I would probably draw your attention to it if you're not already familiar with it, is the Nordic codes and Henry Pearson's textbook, Silo Fires, is probably as up-to-date a publication as there is, that is backed up by full-scale silo tests, albeit 100 cubic metres, not 112,000 cubic metres, but at least there is a bit of science got into there. And what that indicated was that we could be looking at significantly higher gas flow rates in the event of a fire. So the system is actually designed to go up to 12,000 metres cubed per hour for ultimate fire protection. And we do that by using the standby liquid nitrogen system as well as. So the distribution system is designed to take the PSA generated capacity and up to 9,000 cubic metres taken from liquid storage through the evaporators. And that is obviously something that shouldn't happen too often, which in turn brings its own problem, of course, because you've got to try and negotiate a contract with your gas suppliers to give you a very short-term response, to give you 9,000 cubic metres an hour of liquid nitrogen, but you probably never use it. So it must be a tricky old discussion, that one. But we've obviously got some on-site storage as well in liquid form, but it will need topping up. Now clearly this decision to use nitrogen as an inertant to keep it there all the time during storage because of the size of the store meant that we needed a gas-tight store. So we'd thought about silos, we'd thought about flat stores. It pushed us towards domes. Silos, very difficult at this kind of quantity that we'd need. Flat stores just couldn't see a way of making it gas tight. A dome is inherently gas tight, at least it is until you cut the top off, but we'll come on to that. We did a lot of work with Air Products on nitrogen distribution. So this animation that's running while I talk will show you how the CFD model interprets the gas entering the dome based on this high and low permeability. So we've got lots of different load cases, but this is the one which we thought would be the worst. So we've modelled a very extreme dense, compacted fines rich in the non-flowing areas and very permeable areas in the flow zones. We've exaggerated them because what we wanted to see was, will the gas reach all areas of the dome, and if it does, how long does it take to reach? And the answer is around about 48 hours to get a dome to 95% concentration, so we need it all to go red. And you see the clock's running at the bottom there, so 32 hours at the moment. It's still, some areas you can see there at the wall, that's one of the non-flowing zones. It's taking some time, but it does get there eventually. We also did a lot of work with Air Products on oxygen re-entering the dome. We had a big worry about what would happen when we filled the dome. We've gone to the trouble of filling a dome with nitrogen. It's taken us 48 hours to get there. It's now in production. We're going to have to keep opening the slide valve and putting more pellets in. So they did some good work on the likely effects of opening that valve, perhaps running the aspiration fans for a couple of hours for each train load. And those results have certainly been borne out in practice. I showed you that sawtooth earlier. We do see the oxygen come back up towards 10%, but then we can pull it back down within a few hours, ready for the next train. So back to off-gassing. There's been, I'm not going to attempt to pronounce the authors' names there, but this is a paper that's out there in the public domain. It's obviously based on lab-scale work, but it's based on lab-scale off-gassing. And the gist of the paper is that the off-gas rates are entirely predictable. Okay, it takes a few days to stabilise, so fresh pellets liberate more carbon monoxide than older pellets, but once they've aged, it does stabilise. For sure, depending on temperature, it takes longer or shorter to reach that stable position, but there is a predictable CO2 rate, CO, carbon monoxide, apologies there, linked to different temperatures. You do need, if you're going to predict the level of CO that is normal, if you like, normal off-gassing, you're going to need to know the mass of biomass that you're storing. So the domes have actually got quite a sophisticated 3D scanning system that has to deal with some really complex flow patterns. There's 16 outlets there on a W-shaped floor. It's filled centrally, and we reclaim almost individually from the feeders at variable rates. So the operator actually can intervene and bring the dome down fairly level, but inevitably you'll get some fairly deep flow channels. But this system does give us an average of the contents, and it matches very closely within 2% of the inventory measure. So obviously we've been measuring the amount we've burnt and the trains coming in on a daily basis, and we had a 2% guarantee to achieve with this system, and we are there with it. So if we know what the rate of CO should be per kilogram of product at a given temperature, and we know exactly how much product we've got, we can start to think about calculating background CO levels, what's normal. Now this is one of 3 graphs that we've generated with Drax. This particular one is based on 3,000 cubic metres of nitrogen being added to a dome. So it's been aspirated with nitrogen. If you locked the dome down, close the valve at the top, close the valve at the bottom, obviously the CO level will just keep going. You'll never really know what a good level is. You'll just have to use the gradient, the rate of change. But if you aspirate the dome with a given amount of gas, it's not difficult to predict at different temperatures what the ppm level should be in the dome. And this example here, if we had 55,000 tonnes in the store and the biomass was an average temperature of 60 degrees C taken off those multi-point temperature sensors that might not be accurate for a hotspot individually but give us an idea of the dome temperature, that would predict a 1500 ppm background level. Now that's extraordinarily high, you're probably thinking, but that's real, that's normal. We actually routinely run at 1000 ppm in the domes. But remember, this only works if you're aspirating the dome, if you've got some air movement, or you've got some gas movement rather, through the product. So what we've been doing for the last year, really, is validating these graphs. On a daily basis, we'll take measures of what the ppm reading is in the dome, and we've got 8 cells measuring this per dome, and we're plotting it against these graphs, and I'm quite impressed that, these guys got it about right. We're getting excellent correlation with the lab scale predictions of what the background levels should be. So what that allows us to think about is smartening up our alarms. It's not difficult nowadays with SCADA systems to build in these kind of graphs as almost lookup tables. The operators do it at the moment. They know that if they've got 55,000 tonnes in the store and the average temperature is 60 degrees C and they had 2,000 ppm, they'd be in trouble, and that would be triggering some of Drax's procedures to start thinking about controlling a fire. So we can do that, we can replicate that with the control system. We're not quite there yet. We've been spending a lot of time validating these graphs, but we do see flatline CO at predictable levels for a given temperature and a given mass. Well, as soon as you get that, then you've got the possibility of generating alarms. You can start to see the excursions quite clearly. So moving on then from fire protection to dome explosion protection, it almost broke our hearts to take these lovely domes and then break the tops out, but it had to be done. It had to be done. I was aware of a dome in Korea which didn't have any explosion protection. It probably had all kinds of other mitigating measures, but ultimately it didn't have any explosion protection. It was handling coal, pulverized coal. It did explode, and there is no dome anymore. It was a total loss, and you can imagine that that would be catastrophic. So we had to do quite a lot of soul searching about whether we could use the inerting as the basis for safety to prevent an explosion. We're usually less than 5% oxygen in the dome. Well, that wouldn't support an explosion. It's a very good thing to do. It's mitigated the chance of an explosion. But could I put my hand on my heart and say it will always be 5% O2 and not stray up to 8, 9, 10, 11% during filling? We couldn't. And also, DESIR has got an obligation to mitigate the effects of an explosion, not to prevent it, not to protect, but to mitigate. And if you did have an explosion in an unvented dome, it would be catastrophic. It would be like the Korean dome. So we cut the top off, and we replaced the top with obviously a head house and a frangible roof. So this frangible roof forms the explosion vents, which are the ultimate protection for the domes. Now the explosion vents, we couldn't determine the area again credibly by using the conventional formulas, and I'm going to say VDI 3673 again, Dave, and you're going to remind me that I'm just so out of date, and there's an EN standard, and he just told me what it was and I've forgotten it. Thank you. But the point is, again, what an extraordinary piece of extrapolation that would be to use that formula for a 112,000 metre cube dome. You'd like to think it would err on the side of safety, which means it almost certainly would it does. It errs on the side then of something which is entirely impractical, and the size of that aperture in the top would be enormous. So we turned to Gexcon and used their desk modelling, which Paul has already mentioned this morning. He also used at Immingham. This was used to, I'm sorry David, I've just called it desk modelling. I know it's moved on, it's no longer called that, but that was, I wrote it down, it's now called FLAX, but Dust Explosion Simulation Code. This was a model, a code that was developed with EU funding, with the HSE buying into this. So I think it's a reasonably well established model, or way of modelling a dust explosion. I'll see if I can get this one to work. Looks very pretty, looks very effective, looks very interesting. What I was more interested in was the output from this. Of course, it will help us with the predicting the explosion pressure. For the domes, it's about 0.8 bar, doable with a dome. perhaps challenging with a conventional silo, but certainly doable with a dome. What was really interesting for us was the explosion path modelling. So this is the flame front and it's the pressure waves. The domes are fairly well away from the station. You've seen that from the aerial pictures that Peter showed you. But the boiler distribution silos are right in the heart of the station. We've got explosion vents that if we point them up, it's ideal, but we're pointing them straight at the head house. Point them sideways, we're pointing them at other process plants. Almost certainly the bunker house or boiler house are going to come in within distance. And we need to design the equipment that could be impacted for those loads. It's as simple as that. Can be done. For your head house, I'm sure you'll have had some interesting structural issues with that cladding and the cladding rails, but it can be done, can't it? But could you do it without the desk modelling? I don't think so. If I had to resort back to the old design codes where it told me what the pressure was at a given distance, I'd have no idea of what it would be to the side of the path, and clearly the pressure is like a bubble. It's not a fan-shaped explosion vent, it's a bubble, and it can have quite far-reaching effects. So the Gexcom modelling was invaluable for the design of the dome and the BDS silos in particular, and also the dust handling plant, the dust filters and the dust storage silos. We did consider proprietary rupture panels for the domes. We need something like 400 square metres, so you can imagine there's a real challenge in getting some rupture panels on there, being able to maintain them, being able to get at them, trying to avoid cold spots, because we were also well aware of the risk of condensation, and we'd got fantastic insulation in the dome body. What I didn't want to do is compromise that on the roof. Very difficult to detail a steel roof with proprietary bursting panels and still maintain a level of insulation without cold spots at all the junctions. So we decided to design our own frangible roof using off-the-shelf composite panels. So this test here will show you, takes a few seconds to run, so I'll start it running first. This is one of the composite panels being tested by Gexcon again at their facility in Norway. So this is I don't know, something like a 2 metre by 4 metre sheet, which the roof's constructed from. Say composite panels, aluminium cladding, and it gives you an idea, I suppose, of what KST 200 bar per metre per second looks like. And that although that is using some gas of an equivalent KST, wood dust is around 200 bar per metre per second. We believed in the early days we had a comfortable safety factor on that, but looking at what's coming in and what's being tested, we're regularly seeing some products up at 180, 190 bar per metre per second. Southern white pine is the main culprit, but so it is very, very explosive. That is potentially quite a violent explosion. Again, it was really helpful to be able to test the panels and determine exactly how we'd fix them down. We want them to be as weak as possible for the explosion, but I want them to be as strong as possible to withstand snow loads and wind loads in the UK. You can imagine we get some pretty horrendous acceleration of the wind over the top of the domes. So I think I've covered those points as I talked through it. I've got another brief animation here which I thought was the best way of illustrating how the vibrating floor works. So this is the dome reclaim. You've heard a little bit about it. First couple of seconds are just to show you how the inert gas goes in at the bottom and the CO2 could go in at the top if we had a fire. Reclaim by gravity through 2 subterranean tunnels with 16 feeders on the bottom. Each one can do about 300 tonnes per hour. And we can empty out 80-85% of the dome purely by gravity. At that point we start to uncover some sensors and parts of the floor are activated, the product slumps and is recovered, more floor panels are activated, more product slumps and is discharged, and yes, this is an animation, but the good thing about having a very sophisticated 3D scanning system is we can quite easily check whether it actually is real, and we do get complete emptying of the domes as near as makes any difference. We've been in there many times for routine inspections. This is the reclaim tunnel, showing one of the 16 vibratory feeders. They're operating on a closed-loop gravimetric system, so Drax dial in 1200 tonnes per hour, and that kicks in and modulates the appropriate number of feeders. So, in conclusion, why choose domes? Why not use a flat store? Why not use multiple silos? I think storage domes certainly fulfil the need for the large volume storage and large volume gas tight storage, and that was really important to us for fire prevention and helping with mitigate a dust explosion. They're also inherently strong, even when you cut the top off them. So it was possible to increase the design strength, push that up to 0.8 bar, which brings down the necessary explosion area to sensible proportions. So that combination then of gas tightness and a very strong store certainly favoured a dome. The combination of a dome plus this W-shaped floor with this innovative vibrating floor was also the best commercial solution for this particular project. Now, I fully understand why that wouldn't work potentially at Eon's facility, given the life of that facility, and I fully understand why it probably wouldn't work at an import facility. There are other considerations. It just worked for Drax, worked for that storage volume, and it was the most economic solution. So, thank you very much. I think